So welcome to my talk. It's about Cython, as the title suggests. Thing is, I regularly speak at Python conferences here and there and tell people about Cython, teach them a bit here and there. I had a tutorial on Tuesday here. Don't know if anyone attended it. Yeah, still a couple of people, cool. So question now to the audience. I can present a couple of different things depending on what you want. Who's interested in a general introduction to Cython, understanding a bit what it is, who's never used it and wants to know what it is? That is quite a number of people. So the actual topic that I proposed for today was more like, I have some Python code and I want to optimize it without losing the ability to run it in Python. So compile it, speed it up. That's a bit of a less general topic. Who's interested in that? Who came for that? That's about the same number of people. Wonderful. Okay, so I'll just jump back and forth between whatever I can tell you. So yeah, hi, I'm Stefan Behnel. Quick intro about myself. I'm a software or data engineer, if you want. I'm also a trainer. So I'm giving Cython trainings here and there. If you want me in-house, just talk to me and I'll can come over and teach you people there. I'm using Python since 2002. I'm a Cython core developer. Ever since we forked the project from an existing project at the time. Who knows Pyrex? Heard of the name before? Yeah, about a dozen people. Yeah, wonderful. That's what we forked, and Pyrex has basically not been updated much since then. So we've pretty much taken over the project, and everyone's using Cython these days. But thanks, Greg, for writing Pyrex, because it was a wonderful tool to build Cython on. So I do trainings, I do consulting, and I actually joined TrustYou, spawned at this conference last year. And as a motivating example a bit, I'll tell you what we do. So if you look for a hotel in Google, you'll see something like this, right? You'll get a lot of information about the hotel. And if you click around a bit, you'll also see that some of this information was actually provided by TrustYou. So we know what a hotel is and how good a hotel is. How do we do that? Well, we crawl the web, and we have partners, and we read hotel reviews by actual people all around the world, collect them at a rate of about 3 million hotel reviews every week, and then we do text analysis on them, we do data processing on them, and we do that in lots of different languages, including Spanish, Thai, Mandarin, Japanese, lots of languages, and build this kind of information from it. So we summarize all this. There's a meta review, so just a summarization of everything that 45,000 people have been saying about a hotel in this case, and we can tell you what is special about the hotel, what people like, what people dislike, all of these things. You can actually go to trustyou.com, enter a hotel name there, and see this information about any hotel you want, pretty much all over the world. So TrustYou loves Python, loves data. We all do all of the data processing in Python, and we use the usual tools you would expect. We use NumPy, we use SciPy, scikit-learn, pandas. We use Spacey to a certain extent, LXML for the data extraction from the web, and many of these tools actually use Cython, are implemented in Cython. Some of them completely, others mostly. And they're part of the Python data ecosystem. So why is that an ecosystem? Well, it's an ecosystem because it's integrated. Okay, everything works nicely together, it chains together. And a big part of that came from the fact that people developed NumPy as basically a data integration layer that all of these tools could use, could put their data into, could use to share their data across some different libraries, even pass the data on into C libraries, into native code to process this data. So NumPy integrates the data layer, and you can say that Cython is the way to integrate the code layer, because what does Cython give you? It allows you to talk to native code. It allows you to use all these tons of native libraries, C libraries, Fortran libraries out there, connect them to Python, use them from Python, integrate these libraries from your Python runtime. Okay? So when NumPy integrates the data, Cython integrates the code. So what is Cython good for? Well, it integrates native code into Python. That's one use case. Many people use it to speed up Python code by compiling it into native code. And surprisingly, many people actually use it to write C code without having to write C code. Okay? Because writing C code is actually hard. Writing Python code is much more fun, and Cython allows you to write Python code that translates to C, so writing C without writing C. So we write the C code, so you don't have to. Well, topic for today is speeding up Python code, so I'll kind of focus on that. Why you use Cython in general? It's a very pragmatic programming language. It's actually a programming language, so it extends Python, but it is Python. You can take arbitrary Python code, drop it into Cython, compile it. It usually runs faster. But you can also use extended syntax or type annotations in there to speed up your code, to tell the compiler how to optimize your code beyond what the Python language allows. So it's an optimizing compiler. It's actually very production proven. It's used to run, I've showed you a couple of tools that uses. It's used to process, like terabytes, maybe petabytes of data out there in all sorts of Python libraries. It is really widely used, and the cool thing about the language is that it's really about getting things done in the same way that Python is, right? It keeps your focus on the functionality rather than having to look into all the boilerplate that you would need to talk to a C library or to speed up your code, to optimize it. If you optimize your code by rewriting it in a native language, in C or C++, it gets really messy. Right? It's way more difficult than taking your existing Python code, your tested Python code, and just making it faster rather than rewriting it. So the main property of the language is actually that it allows you to freely move between Python and C or C++. So it takes Python code, but it allows you to mix in C data types or C++ data types right in your Python code. Okay? And that's the way for the compiler to decide that you as a user, you were actually opting out of Python semantics, Python object operations, and saying, all I really need here is a calculation with C doubles, right? Native data types, be fast. I don't care about object operations anywhere. I don't want to pass around stuff through Python, and so just make it fast, compute it as fast as you can. And the language makes it very easy. So it allows you to write code that's as Pythonic as you want, but as low level as you need. Okay, first demo. Does everyone know the Jupyter Notebook? Who does not know it? Nice. It's just, Jupyter is just wonderful. It's a wonderful piece of software. It's a very interactive way to do programming, even data analysis. Lots of people use it to play around with data, visualize it in their browser. And one cool thing of Jupyter is that it does not only support Python, it supports lots of languages. Last time I checked, which was like years ago, there was already a dozen languages more. It's probably way more now. And one of those languages is Cython. All I have to do in Jupyter to make it support Cython is load x Cython. And I should restart my kernel to show you that it actually works properly. There you go. Clear the output. Okay. And then just a quick overview of what I'm using here. Latest Python release, latest unreleased Cython. yeah, I'm a core developer. I can take the risk of using an unreleased Cython version in the talk. Some NumPy version, GCC 7. And important bit to understand is, in Python, when you write a Python code, you write a module, you save it, you say Python import, blah, and it just imports and runs. In Cython,
yeah, we see that your Cython version is 0.29. Does it mean it's still beta version for like everybody, or it's not?
It's an alpha version. Oh, you mean 0.29?
Yeah, the 0.29 part.
Well, it's production proven, but we still say it's 0 point something because so at some point, ages ago, we said that version 1.0 should be the version that runs arbitrary Python code. And we still have 1 or 2 bugs in there that where we have to say, well, we have to fix those first before we can say that we can compile any Python code out there. And so it's still at 0 point something, and we haven't reconsidered the goal for 1.0. I think we should, because no one cares about full Python compatibility. Actually, it's it works, it's perfect, it's wonderful, and it's just it's 0 point something.
Especially, it may be hard for to convince your boss. And yeah, let's use Cython, and then he checks, and it's like 0 point something. So it's like
yeah.
It would be probably a good.
Okay, I consider doing like Chrome and Firefox and just say, this is actually not 0.29, it's 29 point something. There you go. Okay, anyway. Quick intro. So here's a bit of Python code. I say from math import sine, so I'm using the sine function from the Python math module. I calculate sine of 5. And it says, well, that's about -1, more or less. So it works. Now, in order to do that with Cython, I can just add this line here, which instructs Jupyter to compile this cell in Cython instead of just push it into Python, run it there, compile it in Cython, and it builds an extension module from that that it then imports. Okay, so it builds a shared library, and that is also something to keep in mind with Cython. You step away from the simple write code, import, try, to write code, compile, import, try. Okay, so there's a build step involved from that point on. It's usually worth it. Okay, so run it. It's actually pretty quick, apparently. I think it was pre-compiled before, so Jupyter caches these cells if it knows that they didn't change. You see a little change in here. What I did before up there is I just said sine of 5. And for Jupyter, what Jupyter does is, it takes the last expression, the last value that fell out of your cell and displays it. For a Cython compiled cell, that does not work. Why? It's an extension module. It's native code. It's external. Jupyter can't look into it. It doesn't know anything that falls out of it. There is actually nothing falling out of it. Just it gets executed. It gets imported, and it's imported as a module. But there's no value that comes out of the runtime. So if I just run this, it would display nothing. But I have to be explicit then and say print this. Okay, one difference. This is still, it's a bit boring, right? I'm doing the same thing. I'm taking the Python function, calling it. It doesn't make a difference if I call a Python function in compiled code or in interpreted code. It's pretty much the same thing. The nice thing about Cython now is I'm not limited to using Python things. Cython takes my code, takes my Python code, compiles it to C. Okay? So what I can do now is I can start using C things because my code ends up in C anyway, and doing C stuff is a totally natural thing to do from C. So instead of importing the math sine function, I do a static import, and this is a syntax extension here in Cython code. So this is no longer Python code, it's Cython code now. I say C import libc math, and that gives me the math header file from libc. Okay, and now I can use the csign function here. Okay, what I'm doing here is I'm assigning it to a Python variable in my module, compiling that, executing it, and question now is what happens when I assign a C function to a Python variable? It becomes a callable, right? A Python callable. Because it's kind of obvious what this should do, right? I mean, I have a function here. Cython can see the function's signature, and I want it to be a Python thing. So the most obvious thing to do is convert it into a Python callable. And what Cython does is it generates code for me that wraps the C callable in a Python callable object.
So you can't call it directly?
I can now call it directly. You'll see that in a minute. Okay. So I have a Python callable now, and when I call it from Jupyter, it outputs the same thing as before. Okay, this is kind of the quickest way to wrap a C function that has a a Python-like signature. Sign is simple. It has just gets a double in, a double out, C double in, C double out. That means from the Python side, you can pass in any float object and get a float object back out. Okay. What this basically does internally is this, spelled out. So this is a long version of this, right? I'm writing a Python function which says, it's called csign, takes a C double, another extension that I can use in Cython now. I can type my arguments. I could just write this, fine. I would do that in Python. In Cython, I can be explicit here and say what I actually want there is a C double. Okay, whatever you put in as an argument should be converted into a C double, and Cython will generate the conversion code for me. So what I'll get here is a Python callable function, which takes an argument, converts it into a C double. I get a type error if that's not possible. So if I put it in a string, we get a type error, obviously. And then inside of my function, I just call the csign function. That's what you asked for, right? And I can do that from Jupyter again, call my Python function, and it runs the sign function internally. Okay. Nice feature of Cython. When I say Cython minus A, what it generates, so it generates the C code for me, but it additionally generates a little HTML snippet for me that shows me how the compiler understood my code. So this is a copy of my code. And it has information that I can use to understand what became of my code. It helps me in optimizing my code. And when I click on one of these lines, I can actually see what C code Cython generated for this line. Okay? This is the function signature. It's pretty involved because it has to do error checking. It has to do argument conversion. It has to do lots of things here and there. It has to register a function callable in the module argument and all that. So this is what comes out of this line. And this line is actually, the second line is actually more interesting. I can see that there's an X argument going in. So we are just, we're mangling the argument names when we generate in C code to avoid naming collisions. This is basically variable X that I put in. I call the csign function on it, and you can see that it's really a straight C call to csign. And then, since this is a Python function, the end result has to be passed back into Python to my Python caller, and for that, it converts it from a C double to a Python float. And this is what this C API call is doing here. Okay. So this is a nice way for me to, for me as a Cython user to understand what Cython is doing with my code, how it's interpreting it, what becomes of my code. You can see that there are a couple of yellow lines in here. And those yellow lines give me additional information. They tell me how much object operations there are in each of these lines. Which is interesting when I want to start optimizing my code, when I want to drop it into C and make it faster there. Because every yellow line tells me there's some object operation going on, there's some exception handling going on, some error checking in that, so anything that uses interaction with the C Python runtime. And if my goal is to convert my code into fast C, not using objects, but using native data types, then any yellow line is probably worth looking at. Okay, and the darker the yellow, the more object operations, object interaction there is going on. Which is kind of obvious in this case. I mean, there's a signature, so like type conversions, error checking, exception handling, stuff like that. Lots of interaction going on there. And this line is really just converting the end result of a C call back into a Python object. So there's less operations going on here. Okay. Now, what makes, and this is just a different way, basically, of spelling the initial example that I had, right? Wrapping a C function, that's it. What makes it more interesting then is, in Cython, once I have a wrapper function here, I can move more code below the Python level. I can take functionality from Python, right, and make my wrapper thicker. I can put functionality into the wrapper between the C library that I'm talking to and the Python API that I'm providing to Python users. So I can make my wrapper more intelligent, smarter, better looking, more Pythonic for a Python user by putting more functionality at the lower level and hiding all the little dirty quirks in a C API that this Python users shouldn't have to bother with. Okay. Simple example here. Instead of calculating just calling the sine function, I call sine of x squared, right? I could do that in Python. I could use my wrapped sine function and do x squared, pass into the sine function, and then would calculate the sine of that. But doing that as C is just much faster, right? I push down the x, it calculates x squared, sine of x squared, and then passes back that result. Much faster than doing half of that in Python. I can do that here, and it runs. Okay. Just two little things. Since we're in C now, I can use manual memory handling in C. This is how that would look like. I have malloc and free, so I can allocate some memory. I mean, in Python, memory handling is completely automatic, right? You have objects, you have references to them, and when the last reference to an object goes away, then the object just dies and gets collected. That is not the case in C, like totally not. C is completely manual. And so in C, I would say, allocate some memory here. If that fails, I can null pointer back, and I just say raise memory error. You wouldn't really do that in C, right? What would you do in C? You would return some error code, right? Say return -1 or return something that tells the caller, something went wrong and you have to handle it. In Cython, well, Cython is Python, right? It integrates with Python, so you can just say, raise memory error, raise an exception from your Cython code, right? Totally normal, and this is totally what you would do. Well, if the allocation worked, then I can use my memory for something, and we have a couple of nice features in the language that make array operations, point operations a bit more, handy and Pythonic than they would be in C. No, so question was, are those bound checked? Yeah. No, because CMEM is just a memory pointer. This is one place in memory, and here I'm actually explicitly telling Cython, to assign something to the first two entries, which is still much nicer than in C. But pointers are just pointers. They're not arrays. Arrays are actually bounds checked. Okay, so I can do this, and there's a couple of nice things. I can also say just print. If anything goes wrong here, then I definitely want to clean up my allocated memory, right? So I want to free the memory, and I do that with try finally, as I would in Python, right? So if print, for example, raises an exception, can't print, no standard out anymore, for example, close already, anything can go wrong here. I'm doing a Python thing. right? So this can raise an exception, and it just, if that happens, I say, finally, still make sure you free my memory regardless of what happens. Yeah, nice feature. Okay, quick example for calling external code. You've seen the libc sign function that I called. Here's an example for calling an external library that is not just there like libc, but really an external library. This is Lua. Who knows what Lua is? Who's used it before? Yeah. Okay. Cool. So Lua is a little. It's really a small language, right? It's a language that people use for embedding, commonly in C++ projects. But you can obviously also embed them in CPython. Why not, right? So here's a little embedding for Lua in Python. First thing I have to do is I have to tell Cython what the C API that I'm using here, the Lua C API, looks like. Previously, you may remember that I said, C import libcmath. What that does is it looks up an external declaration file and finds the libcmath declarations in there. Here, I'm doing that inline in a module. And this is the syntax for it. I'm basically just saying, this is an external declaration. It describes external code, which comes from the lua.h file. So that's the header file that describes the Lua API. And it has a couple of things in there. There's a struct in there. There's a function for creating a Lua runtime, for cleaning things up, for loading code into the Lua runtime, and so on and so forth. A couple of functions. And note that I did not copy the complete vast Lua C API in there. I just copied the functions that I need. Because that is all I need in my code. Remember that Cython translates my code to C, right? And then there's a C compiler afterwards that compiles that to a shared library. And the C compiler obviously sees the whole thing, right? But Cython doesn't need to know about the whole thing. It just needs to know what I'm using in order to generate proper C code that the C compiler can compile and understand. Okay, also very nice. So it's really just a dozen functions here or so that allow me to execute Lua code from Python. So what's my interface? I'm defining a Python function that takes a code as Lua code as a string, and I'm doing a couple of things. Blah blah. Here, it might be Unicode string. In Python 3, it's quite likely going to be Unicode string. In that case, I have to convert it because C doesn't know Unicode; it only knows bytes in strings, and that's how the Lua API works also. So I converted it to UTF-8 to be able to execute it there. Then I create a new Lua runtime. If that fails, I just say raise memory error, because that's what the documentation tells me. If the creation of the Lua runtime fails, documentation says it, well, it's probably a memory problem, right? Couldn't be allocated. So raise memory error is the right thing. And then whatever happens, I use a try finally to make sure I close down my Lua runtime afterwards and clean it up. And this is what I'm doing down here in my finally. So I'm cleaning up the Lua stack and closing the Lua runtime to clean everything up, to release the memory. And then I have a function to pass in the Lua code into Lua. If that fails, I raise a syntax error. Well, probably wrong syntax. Then I can execute my code using the C API function, and I get some result back. I'm being lazy here. I'm just expecting some number back. I could look at what the result is and properly convert it to some corresponding Python type, but here I'm only expecting numbers. Okay, one number result, and that's it. There's a function to converting it to a C number, and then when I return that from my Python function, Cython will see, okay, there's a C number, and you want to return it from a Python function, so I'll return it as a Python object. So I compile this. Here's a couple of lines of Lua code. Recursive Fibonacci, the usual stupid benchmark. And when I run timeit on that, it's going to tell me that Fibonacci of 24 could be calculated in 2 milliseconds, a bit more. Okay? This is how you use C libraries from Cython. Okay. So 10 minutes. So I'll get back here. Second example, optimizing Python code. I chose difflib who knows difflib from the standard library? Not so many people. You should look through the standard library documentation. There's lots of nice goodies in there. So what difflib does is you can pass two sequences in there, and it's going to compare them and tell you where the difference is. It's just like the Unix diff, but at an API level, right? You can use it directly from Python. It's been there for a long time. You know, it's in the standard library. Most things in the standard library have been there for a long time. So I'm going to optimize difflib a bit. Okay, so as a benchmark, I'm using a tool called Fuzzy Wuzzy, which comes with a little benchmark. That's why I'm using it. Fuzzy Wuzzy basically just does fuzzy comparison between texts. Okay, so you pass in two texts, and it's going to do a fuzzy comparison and try to match the parts. And well, it's not really relevant. I'm just using it as a benchmark here. And I'm using cProfile for profiling to see how fast my program is running and where I get. Okay, so okay. Let's look at let's run it first. Okay. I'll just clean up my stuff and then run a benchmark. Yep. So that's taking a couple of seconds. It's running multiple examples, and the timing. So the benchmark is just the time it takes to run the whole benchmark for Fuzzy Wuzzy. Okay. And so you'll see in a minute that it's dominated by the time it takes difflib to do the comparisons. Okay. Takes a bit of time. Okay. One thing you shouldn't forget when running benchmarks is switch off energy handling of your laptop. It's probably okay in this time, in this case, because it's been doing computations before, so probably not slowed down much. Yeah, it's about what I expected. So 46 seconds for the whole runtime. Okay. Now, next thing I'm going to do is I'm running a cProfile on the benchmark to see where the time goes. So I'm going to run it again. It's going to take a bit longer to run. Who does not know cProfile? Okay, a couple people. So cProfile, what cProfile does is basically it traces your code. On each function call, it's going to tell you functions be called, functions been exited, and then afterwards, it's going to present. It's going to dump the profile somewhere, and it's going to tell you what were the functions in there that took most of the time. And like where was most of the time spent and what was less relevant. So it's a very quick way of assessing the runtime profile of your code. And like finger pointing the point that you want to optimize first. Okay, again, it takes a while. Obviously, it takes longer now because, as I said, it instruments your code, right? So it's really doing stuff while your code is running. There are profilers out there that slow down your code much less, and it's really worth looking into them. One is the perf tool in Linux. So if you have Linux, look at the perf definitely. But it operates, most of these tools operate at a much lower level, so they give you C-level information rather than Python-level information. And cProfile just really gives you Python-level information. So I've executed lots of function calls. How many are there? 153 million function calls along the way. It took 78 seconds to run now. And well, the most costly function here is find longest match. In difflib, and it took 25 seconds over runtime all by itself, plus it took an accumulated 34 seconds if you add the its own function calls, so its internal function calls to it. So the whole time spent in that function was 34 seconds, and so function and its own code that it uses. and 25 seconds only directly in the function itself. So that's a lot of processing time. So I'll look into that function, and I have it somewhere here. Can you read this? Is this large enough? Larger? Okay. Like this? Better? Okay. So this is the find longest match function. It's actually a method, which makes it a bit more difficult to optimize, but I'll just do a couple of quick speed-ups here. And it basically starts here. You can see someone's already tried to optimize this function quite a while ago, apparently. This is one of the standard tricks that you would pull in Python. It's a bit of an ugly trick. Normally what you would say is, A in B, and what they do here is they take the bound method of B, so B contains, and say B contains A. Okay, so replace the operator by function call. And apparently that was faster at the time. I actually tested it, and it's still a bit faster in 307. But it's something that you don't need in Cython because operators in Cython are actually much faster. So one thing I would do is remove that. But there are actually quicker gains to make here, and I'll start with those. When you look at the code, what it does is it has a nested loop and runs over a couple of data structures. You don't need to understand what those data structures actually do. It's there's a dict involved somewhere. It keeps track of stuff, dict in a list, and it's doing things here and there. But there's a nested loop. Okay. A nested loop always means that there's a lot of work going into looping, into doing stuff there, and loops are very easy to speed up in Cython because you can replace them by C loops and do stuff directly in C rather than running through Python's iteration protocol. So I'll do that first. How do I do that? Well, this is using a loop over a range. So I know that these are actually integers, and I can replace them by C integers. Okay, most obvious change first. And when I look into the usage of I, then I can see that it's used to index into a data structure. It's used as key in the dict, and it's also used as index somewhere. And that means that so a difference between C integers and Python integers is that Python integers are unbounded. Right? They can have they have an arbitrary value range. They can be as large as your memory allows. C integers are not. C integers are always range bounded. So this is a 32-bit integer, which can take numbers up to 2 to the 31, stuff like that, if it's signed. When you're converting Python code to Cython now, to faster C code, you have to take care of that, right? So I'm replacing Python integers, safe Python integers, which can go arbitrarily large, by bounded C integers, and I have to make sure that I'm not restricting the value range in an invalid way, because C integers wrap around and do weird stuff when they go out of bounds. But there is a C integer type that I can use here, and that is it's called PySizeT, or size T if you want, which is defined to be large enough to fit the size of memory. So it's on a 32-bit system, it's 32 bits. On a 64-bit system, it's 64 bits, and so on and so forth. And I'll type all variables in here using that type. I'll actually use a different type. It's called PySizeT, but that's just a different name for it. That's used in the Python world. I'll use that for my integer variables, and I'll type them in Python annotation syntax. So I have an I have a J as an index. I have, what else do I have? A low, a high. So they're all index variables here, and there is B low and a B high when I look through my code. Okay, those are all the index variables that are being used here. And there's also best size, which is also just an index. Best I and best J. Okay, yeah, all of them. Best I, best J. Okay. Yep, I'm through with my 40 minutes. I'll just go a bit into the question time and then run this there. So I'll first compile it. I'm using Cythonize here, so compile my difflib. What it does is it just generated a C file for me. Now it's calling the C compiler. So Cythonize is a nice tool for doing like all in one, right? You say Cythonize my code, Cythonize -i, so build it in place, compiles it, generates the shared library for me, and you can just import it. And now when I run my benchmark again, it's gonna take a while. It's gonna be a lot faster already. And while it's running, I'll look into the code again and just tell you that there are a couple of more things that we can do. One I already mentioned is I can replace this Python hack here by just the expected operator. So undo a Python optimization that is, that you can do, but that is not beautiful. And and a couple of other things are, I'm using dicts here, for example, dicts and lists. Here, I'm calling the get method of a dict, which in Python is looked up every time. In Cython, that's actually very fast if Cython knows that B2J is a dict. And so if I type B2J as a dict, which is the next thing I can do, is that actually, that is probably an argument. Okay. So B2J is a dict. It's a Python dict. Then that's also going to be sped up. And you can see we're down from 46 seconds to 35 seconds just by typing the integers. And one thing that did is it allowed Cython to replace this integer range loop by a C for loop. Okay, because all the index variable is typed, so it knows that there's nothing that can wrong. We're asking for C for loop here. Okay, and I'll try the dict optimization next, and then I'm already through with my talk. And there should be time for 1 or 2 questions afterwards. So it's compiling, run the benchmark again. Okay, and this is the usual way how we go about optimizing code in Cython, right? You take Python code, you start typing variables, replace them by C data types here and there. You use static typing for instructing Cython to opt out of general, this is some kind of object semantics, into this is a specific data type, please optimize it, optimize the code for it, and Cython will generate code for the data types that is usually faster and definitely more adapted to what you're doing in your code. Okay, and that gave us another 5 seconds runtime. So we're down from 46 seconds to 30 seconds just by typing a couple of variables here. Okay, and that's it.
We got time for a few questions, 1 or 2.
Just a couple of questions.
Yeah.
The first one is like we have seen that you can call random, custom C libraries from Python just by defining the interface for them. Is it possible to do the opposite? Call Python code from C with using Cython?
Yes. You can generate so-called CDEF functions in Cython, which are just C functions with the expected C signature, and you can drop any Cython code in there, any Python code in there, and you can call the C function from C, and then you can execute any Python code in there.
Oh, cool. And the second question is whether Cython benefits in some way from using typing hints, like in new Python we have the function type hints and so on.
Yeah, I've used the syntax for this. It does not really benefit all that much from normal PEP for type annotations in Python, because there's not so much to gain from them for optimization. They are for code checking, they are not for optimizing code.
One last question. So we use Cython a lot. It's a really great tool. One of the things we miss in the Cython ecosystem is a linter, some kind of like Flake or Pepe or whatever. Like we use some subset of what Flake does, like basically ignoring syntax errors. But we wonder if there is any project or idea of maybe exposing the abstract syntax tree or something, so we can hook into existing linting tools.
Okay, so tool support. You can do two things. One is, as long as you're really just optimizing Python code, you can use Python syntax for it. And that keeps your code, your optimized code, your compilable code in Python syntax, and you can use all your Python tools. As soon as you start calling into C using native code, you lose that ability because it can't be mapped to Python, and that code cannot run in Python anymore. So you use Cython syntax for that, in which case there are a couple of, well, there's at least PyCharm, definitely, which supports Cython. You can use that. There are probably also other IDEs who are, kind of having some basic support, or, but I'm not aware of many tools for code analysis and this kind of stuff on Cython code, specifically Cython syntax.
All right, don't forget to rate the talk, and let's give Stefan one round of applause.